Okay, yeah, so the whole last week and yesterday we've wrapped up the topics on finding long path or cycles in pseudo-random graphs and or GMP, the binomial random graph. For the rest 3 days, including today, we will talk about a different structure, trees, embedding trees. So after path and cycles, the other simplest structure that we can find will be trees, right? Um, in a sense, trees is acyclic, so could be considered even simpler than graphs with a cycle. Um, but as we will see, that lots of techniques that related to this Friedman-Pippinger that we will cover, you will see some similarities with what we've seen on this Poch's rotation extension. In particular, the expansion derived from randomness play an important role, basically. Okay. So, right, let's get to it. So this is a new topic now. First, I would like to, so the plan, okay, maybe let me lay out the plan for the rest 3 days, just to have an idea of what will be covered for the rest of 3 days. First, we will cover the classical Friedman-Pippinger theorem, okay? We will cover this Friedman-Pippinger theorem on trees, on embedding trees. So this will give us relatively large trees, but not extremely large, as we will see the precise statement. Then we will prove that, in fact, almost similar identical proof allows us to embed almost spanning trees in graphs. Oh, by the way, all trees are bounded degree, okay? If I'm not, the whole time, all trees have bounded maximum degree. We will just talk about bounded degree trees. Okay, we will not talk about trees with high maximum degree, go beyond constants. Okay, so after introducing the Friedman-Pippinger and proving it, and we will see that exactly the same proof actually works for almost spanning trees. So we'll talk about almost spanning. Recall that spanning means you use all the vertices in the graph. Almost spanning means it's a tree that occupy 99% of the vertices. Okay, almost spanning trees. In particular, we will find this in expanders and in GMP. We look at the threshold. Then at the end, we will look at spanning trees, spanning bounded degree trees, and present a proof of the threshold. So we will present a weaker proof because the full statement goes beyond this lecture. We will prove a threshold for spanning trees for a single tree up to some polylog factor. Okay, this is the plan. We'll go in according to the size of the tree, from median size to almost spanning to the spanning. So let's first look at what is this Friedman-Pippinger theorem. Basically, after Poch's rotation extension technique, people see that you can use expansion property to find long cycles. Recall that one form, okay, just recall one version of one consequence of Poch's rotation is that if you have an expander in which all sets of size up to k expand by a factor of 2, so if you have a 2 comma k expander, this means all sets up to size k expand by a factor of 2, then you can find the cycle with the length at least 3k, right? This is one of the corollary that we derived last week from Poch's rotation. So people see that, okay, you can use expansion property to find a long cycle. Then what about large trees? This is what Freiman and Pippinger managed to do. It's a very classical, by now, a classical result, and it's used in many places. Let me state the results. Okay, let me first define the not very standard notation. Is I define gamma of x to be the neighborhood of x. Okay. So this is not the external neighborhood. Recall that usually when we write this, n of capital X, this is the external neighborhood, which is the neighborhood minus itself. So actually, the whole proof here with little differences, you can exchange these two. But since the original proof and many references afterwards, they stick with the neighborhood gamma of x instead of n of x. So I try to stick with the original presentation. But just keep in mind that these two are roughly the same. Not going to affect much when we work with random graph. There's lots of rooms. Okay, so once again, gamma of x is the u. So this is x. Okay, you could have neighbors here, and if this is a neighbor of itself inside, then this guy is also in. Both of these two is also in gamma of x, right? Slightly non-standard, but okay. So then in this notation, Freiman-Pippinger's theorem states that, so you can compare to this statement up here, okay? This color is not good. You can compare to these. They look kind of similar. Let dm be natural numbers, positive integers, and g be a graph, okay? If we have the expansion that the neighborhood of x expands by a factor of d plus 1 times x, okay? So instead of expansion factor 2, now we require expansion factor d plus 1 for all small sets up to size 2m, okay? Then what's the consequence? Then G contains every tree on m vertices with maximum degree and most d. Okay, so basically, if you have the expansion property for small sets, then you contain small trees, small boundary degree trees, all the small boundary degree trees. Okay, so if we want to write it in terms of this expander notation up there, basically it looks more and more similar. In that notation, we can say that since external neighborhood is a subset of neighborhood, right? Then we can rephrase what's up here as 5.2 if we have a d plus 1 2m expander, right? Sets up to size 2m, expand by a factor of d plus 1. Then we have all m vertex tree with max degree and most d, okay? It's basically the same thing. I just write it in terms of expander, maybe it looks more concise. So the proof I'm going to present here is almost the same as the original proof by Freiman and Pippinger. I will present a slight adaptation, just change a little bit, okay? Change it a little bit so that later it can also be used to find almost spanning trees. So this adaptation is by, we will present adaptation by Glebov, Johansson, and Krivelovich. Okay. So for the proof of 5.2 or 5.1, in one sentence, the proof is kind of natural, okay? So what we do is, in one sentence, we kind of do a strong induction in a sense, meaning that using the expansion property and given a bounded degree tree on m vertices, we will embed this tree one vertex at a time until we finish the embedding. Okay, just one vertex at a time. We add one leaf at a time and finish it. But why do I say it's kind of like a strong induction? We will make sure that at each step, when we add a leaf, the current embedding maintains some nice property. Okay, so it's kind of like a stronger hypothesis in that sense. So let me make this precise. Okay, so a key definition according to this adaptation, so the idea, let me write it down, what I just said, is to embed the tree one leaf at a time and try to maintain nice. Okay, let me make it not very rigorous. So now let's make it, so what do I mean by nice? It's captured by this definition, so-called DM extendability. All right. So let's let, okay. Let DM be integers, positive ones, where D is at least 3 and M at least 1, okay? And G be a graph. A subgraph S in G, this is a subgraph, is DM extendable. This means it's a nice partial embedding, okay? So how can it be nice? Extendable if two conditions, okay? The first one is fairly easy. S has maximum degree and most D, same as the tree. Recall that we're embedding a tree with maximum degree D and most D. So this is okay. This partial embedding also has bounded degree. Second is the key definition. And, okay, bear with me for a moment. It looks a little bit technical, but we can try to make sense out of it. We define Bx as to be what? To be the neighborhood of X in G out of the vertex set of the subgraph S, okay? Not in our current partial embedding S, minus D times X minus the degree of X in the partial embedding S, where you range X in the intersection of X and V of S, okay? So let's just write this down for now. This is at least, this is non-negative. We require this for all vertex sets, subsets of size up to 2m. Okay? And furthermore, we will call this guy, we call it the balance. This is called the balance. S balance of X. It's a little bit long notation. Okay. And we call X is as critical if the balance is at the threshold point at 0. And X is not big. A small set with balance 0, we call it critical. Okay, so let's digest this notation. It looks a little bit technical, but actually it makes sense. So the most technical part is here, basically, right? Well, once again, we call a subgraph S. This subgraph S will be the partial embedding that we have so far. Then we call this partial embedding good, which we term it DM extendable, if this weird balance inequality holds. It's at least 0. But if you look at the first term in the definition of BXS, what is it? Let's draw a picture, okay? I have X here. I have some partial embedding S, okay? It could intersect S, I don't know, something like that. This is my S. This is the partial embedding that we have for the partial tree or forest. And now we require that the balance to be non-negative. What it means is that the neighborhood of X out of S, so the neighborhood of S out of S, we look at its neighborhood, which is here, right? We want this guy to be at least as big as, so first of all, this blue guy here, gamma of X minus V of S, is kind of like the good vertices we can use, because these vertices adjacent to X, so if ever some vertices in X is used in S, we can extend it by attaching to X, right? So these are the good vertices we can use to extend the current partial embedding. Then the second term here kind of explains the responsibility that we have for X. What it means is that if the whole X is in S, is in the partial embedding, then since the tree has maximum degree D, so it could be that all the vertices in X are responsible for D connections, for D edges incident to it. So we need to have this much neighbors attached to X, right? D times X. But of course, some are already done. So we minus some already embedded. The second term here, subtracted from D of X, is those with already the neighborhood of X in S in the partial embedding. So this difference here, which is the whole second term, is the remaining possible upper bound for the remaining possible leaves we have to attach to X. So if the first term, which are all the available vertices, is at least as big as the second term, then for sure we can extend it, right? So this is what I mean by the strong induction hypothesis, that this partial embedding is very nice, okay? So the whole time we just need to make sure that we can embed the tree one vertex, one leaf at a time, and make sure that all the partial embedding S during this process, they are nice in the sense of DM extendable. Okay, then you just embed it one by one. So this is captured in this lemma. Oh, so before I write down lemma, just quickly. So I call this S balance, this BXS. Balance means how much wiggle room we have, right? And critical, so of course the critical set we have to be a little bit careful because they are exactly 0, not the balance. So we have to pay more attention. When it's strictly positive, then we have some wiggle room. This is why we need to define it separately, the S critical sets. So this lemma 5.4 is the proof we will prove today. A little bit technical, but the idea is quite intuitive. It's basically what I have explained. What I have explained. We try to embed it, while maintaining this nice embedding property. So 5.4, let DM be natural numbers. Okay, some basic things. and we have G, a graph, and S is a nice subgraph. Is DM extendable subgraph. Now, suppose, okay, we have this basic thing down. Suppose we have the following expansion property, that the neighborhood of X is at least D times X plus the order of the partial embedding S, the extendable subgraph, plus 1. So again, some sort of expansion property for all small sets X. Here, we require just between M and 2M is enough. We don't need it to be all the small subsets, somewhere in the middle, M and 2M. Then, the conclusion is that then for every vertex S in our nice partial embedding, capital S, as long as its degree is at most D minus 1, so the maximum degree of the tree is D, so D minus 1 means there's possible another leaf we need to attach to it, okay, D minus 1, then there exists a vertex Y in the neighborhood of this vertex in the nice partial embedding minus those that we've already. So we don't want to embed into the partial embedding. We don't want to create a cycle. So you always go outside, minus V of S, such that the graph S plus this new edge, you extend it by adding Y to it. This is this notation. Is again, I hit some button, that's why. Like this. Oh, if you hit this button, it rotates. I see. So is again extendable, a nice partial embedding. Okay. This is precisely what I have described before. We have a nice partial embedding S, given some expansion property here. Okay, for some sets in certain range. Then, for any vertex that have not yet meet its quota, okay, the degree in the partial embedding is MOT minus 1, then we can always find one of its neighbor out of the partial embedding, attached to it, adding this leaf to extend this partial embedding while maintaining this nice property. This is lemma 5.4. And so for the remaining time, we will prove this. We can finish the proof today. Then if we have time, we will derive Feynman-Prippinger. Otherwise, we derive it next time, which will be really quick. Derive it from 5.4. And from this lemma 5.4, we can also quickly determine the threshold of the containment of almost spanning tree bounded degree in random graph. So this is a key lemma. Okay, so once again, if it's extendable, then we can attach the leaf to make it extendable. Recall the extendability, extendable notation is that the available vertices, which is gamma of X out of the partial embedding V of S, is at least as big as its liability, which is the possible upper bound for the remaining vertices that have to be attached to X. Okay, this in this blue blob. So The proof is relatively intuitive, as in every step kind of justify the next step. Just a little bit technical, so let's go through it. So basically it goes as follows. Before I give the details. So suppose this is S, this is our partial embedding, okay? And suppose S is the vertex that we choose with degree at most d minus 1. And now we want to extend it to another nice embedding. So basically we say that, okay, you look at all its neighbor in G. This is its neighbor in G out of V of S, okay? If for all this neighbor yi, none of them adding which to S extend to a nice embedding, we will derive a contradiction that the original embedding of S is nice, is DM extendable, okay? Which by contradiction means one of these neighbor outside, there exists one little y such that we can add it to make it extendable, okay? So we will show if none of such y extend S, then S is not extendable to begin with, okay? Which is a contradiction because we assume S is extendable, DM extendable, okay? That's basically the idea. So let's prove it. So let's let formal proof, let Y to be this set, to be this set here, okay? Which is the neighborhood of S. When S is a singleton, gamma of S or n of S is the same, external neighborhood, because S cannot be adjacent to itself. So let Y to be the neighbor of S sticking out of our partial embedding S. And then for shorthand, let me write S sub Y to be the graph obtained from S by adding one of these leaf, S little y, for Y in Y, okay? So this is the shorthand. Now we assume for contradiction that none of the S sub Y is DM extendable, okay? First, I have to show that Y, capital Y is non-empty. What if you have nothing sticking out, right? That's a problem. So this is where we use the fact that the degree of S is at most d minus 1. So let's first prove that Y is well-defined, non-empty sets. This follows basically, okay, let's see Y is non-empty. As S is DM extendable, and the degree of S in our partial embedding is at most d minus 1. We have that. So recall, what does it mean S is extendable? That means every small set has non-negative balance, right? Let's recall this notation here. The balance is B of XS. For every small x, with respect to S, it has non-negative balance. So we apply that S is good to then that means in particular, the balance of the singleton set, little s, has capital S balance non-negative, right? So this is at least 0. This is by the DM extendability of partial embedding S. So let's write down this. By definition of this balance, this basically equals to exactly ng of S minus V of S. Remember, this is the available thing sticking out, which is exactly Y, basically. Minus its liability, which is now S is just a singleton. So it's D minus ds of S. Okay? Recall that let me recall one more time. So usually is bxs equals to, this is the first term, minus, so the appropriate vertex x in x-intercept v of s. D, what is this? D of x minus that, right? So here, x is singleton little s, so we have that. Then, this equals to y minus d plus that, this is at most d minus 1. This is y minus 1, yeah? So we get that y minus 1 is at least 0, which means y is at least 1. Implies that y is now empty. Good. Now, okay, suppose for contradiction that none of sy is dm extendable. If one of them is extendable, we are done. This is what we want to prove. So suppose adding any one of these sticking out vertex to S does not maintain this extendability. What does it mean, first of all, by this assumption? Not being extendable, that means some small set whose balance falls negative, right? Being nice means all the balance of small sets is non-negative. So not being nice means some sets. So this in particular implies that for each y in y, there is this some small set, which I index it by capital X sub y, some small sets of, by small I mean up to size 2m, such that its balance is negative, okay? Its balance of this small set with respect to our one larger embedding, partial embedding is false negative. This is what it means that S sub y is not extendable. So then we will play with this capital X sub y and derive a new set which has negative balance with respect to S, which will give us the contradiction that S is an extendable subgraph, okay? So all we need to notice, well, first of all, to make use of this information, that the balance, sy balance of xy is negative, we have to study the change of balance when we extend the partial embedding by one vertex, meaning that I claim that B, if you look at the balance of the set x sub y, with respect to the balance of x, its balance with respect to one smaller embedding. So you look at the S balance and S sub y balance, what's the difference? The difference is minus, let me write it down. The indicator of y is in the neighborhood of x sub y plus S is in capital X sub y plus y is in x sub x. This is very easy to verify. I will just write down very quick some reason. I'll leave the verification as exercise. It's quite dry. Basically, just check the definition of the balance and look how adding one more vertex y changes the balance, okay? So this proof is basically, it follows from, let me write down the reason. The fact that if you look at the balance, the first term is what? is the external neighborhood out of the partial embedding, right? Look how this changes. You first look at the first term, how it changes. Neighborhood out of the partial embedding, it only differs when y is in this, okay? Otherwise, they are the same. This is very basic. And the second thing you use is that the sum of x in capital XY intersect v of sy ds sub y of x, lots of indices, equals to, now let's see how this changes. Okay, so if you see how this changes, now I change it to okay, I first change this to this. Now I'm going to change this to S. This can be easily verified just by definition. Now then we have the difference of the second term in the balance, right? Then basically you combine these two, you can get this claim. I will not verify it. If you just write it down, it's easy to check. This claim basically by definition. Now, okay, but what does it, how do we use this claim? What do we know? Well, we know that the left-hand side, the balance of this set x sub y is negative with respect to s sub y. Okay, this is by our choice of capital X sub y. But we also know that S is a nice embedding. In particular, that means the balance here with respect to the previous embedding, it should be non-negative. Okay, so when you fall from non-negative to negative, what it means is that we have to subtract 1 here, meaning that y has to be in here, the neighborhood of capital X sub y. And both of these two has to be 0. Otherwise, you don't fall, you don't decrease, you don't drop. Okay? So let me write it down. Thus, to have the balance to be negative, we must have, we also must have this balance here has to be 0, because if it's at least 1, we minus at most 1. And this is not negative, so this the left side cannot be negative. So the balance of, we must have 1 of capital X is 0, okay? And we just need 2 of this condition. We don't need all 3 indicator to be 1. We just need, I write down the 2 we need. Y has to be in the neighborhood of capital, right? And S cannot be in capital X sub Y. Okay, we will use these 3. So this means XY is S critical, right? We call it critical. It kind of makes sense when you just extend the embedding by adding one more vertex from S to S sub Y. This balance change very little. So the only chance it becomes negative is it was before critical. So then it falls negative. Okay, so this is why we have to be a little bit more careful with critical sets. So for critical sets, to make use of this information here, okay, we have to prove this claim, which says that about critical sets. All S critical sets have size 2 property, have size at most M. So remember that originally we only require sets to be size up to 2M, right? We only require it to be up to 2M. But in fact, we can get a tighter bound for critical sets. It's actually cannot be bigger than M. Second, as critical sets, they are closed under union and intersection. Meaning that if we have X and Y, they are S critical, then S union Y and S intersection Y, these two sets, they are also critical, S critical. Then by the first item, again, S union Y is at most M size, for example, we can use that. So the proof of this is also not hard. Basically, you just go around the definition of criticality and carefully analyze how the balance changes. So let me skip this for now. Not particularly illuminating, okay? It's basically by definition. But let's first see how this claim finishes the proof. Let's assume this fact about S critical sets. Then we will derive our final contradiction. Okay, we define a set X star to be the union of these small sets that witnesses that S sub Y is not extendable. Okay, we take the union of these small sets. Then what do we know about this X star? First of all, recall that each one of these little witnesses, this guy, they are S critical, right? And since criticality is closed under taking union, so if you take the union of all these small critical sets, X star is also S critical. Okay. Good. And in particular, I don't know if this is used later. Okay, let me not write it. So X star is S critical. And what else? Okay. Now, let's again look at another one I want to write down. If you look at the neighborhood of little s sticking out, which is our set Y, right? Recall, this is this blue set Y that we defined. The neighborhood of S sticking out here. Okay. If you look at this set Y, it must be a subset of neighborhood of X star. This follows from this guy. Yeah. Ding. Because, right, what is capital Y? Capital Y is the union of little y, right? And every little y is in the neighborhood of capital X sub Y. So since X star is the union of these, so the union of Y is falling here. So this is one places you can see that why we stick with gamma of X instead of external neighborhood N of X, because gamma of X is additive, while N of X, the external neighborhood, is not completely additive. So it's a little bit annoying here if you work with external neighborhood. But anyway, so we have this property also, okay? And we also have the last property that little s is not in this set that we just defined. Little s is where we want to attach this leaf y, right? Why? It follows from this guy. What did I just do? Okay. I'm running out of symbols. Upside down star. Heart. Because S is not in every single guy consisting of X star, so we have this one, okay? This is by this one. Okay. Now let's proceed to finish it. I think we're kind of on time. We're almost done. So as you can see, even though it's a little bit technical, but basically you do what you're supposed to do, right? Suppose none of this extension is legit. Then we try to find the set that witnesses that our original subgraph S is not legit, okay? Okay, after obtaining this, consequently, according to my note, so let's see what is consequently, we have that gamma of G of X star, oh, okay. So our magic set will be X star union S. We will show that X star union S, we should see this guy shows that capital S is not good. We will see, should see this guy has negative balance. Which is a contradiction because all small sets has to have non-negative S balance because S is a nice embedding, extendable, right? So let's see that. So let's look at this guy. Well, first of all, if you look at the balance term, the first term is the neighborhood of this guy is sticking out of V of S. That's the first term. It actually is the same as X star minus V of S. Why is this? Let's see. The only difference of left and right hand side is the neighborhood of S sticking out of V of S, which by definition is exactly Y, right? But we know that Y is a subset of neighborhood of X star. So it's already included here. This is why we have the equality here. All right. Next, we have to look at the second term in the balance in the definition of balance, which is the liability, right? Well, we have that D, the second term is D times the size of sets minus sum of the degree. So let's first look at this guy. Well, this guy is fairly easy. We just write that. This is just because S is not in capital X star. So we actually increase the set size by 1. So of course, we have that. Now, X star is S critical, and our degree is most D minus 1 implies that, let's look at the last term, which is the degree. Okay, actually, I just put everything together. So let's just write everything together. We look at the S balance of our new set. If you compare it to X star balance with respect to S, the difference is that, well, the first term are the same. So this cancel out. The second term differ by a D. So let me write minus D, that's the second term, or the first term in the second term. Then you look at the degree sum difference. Okay. Because X star is S critical, so this is 0. Okay. This equal to 0 minus D. And you look at the last two terms, the only difference is the vertex S, because the set only changes by singleton S. But our vertex S has degree at most d minus 1, so this is at most -1, which is well, almost contradiction. We have to show that X star units S is not big. S is extendable means that all small set up to size 2m is extendable. But this is also immediate because X star is S critical, and all critical set has size at most m, right? By the claim. So our new set has size m plus 1, which is at most 2m. Now we get our contradiction. We have defined a set X star union S, which is small, at most 2m, which is negative S balance, okay? Contradicting to S being dm extendable. Yeah, I think I running out of time. I will not prove this claim about critical sets. Assuming this basic claim, we basically see all the details of this proof. I'll leave this, it's not so hard. You can find it in my notes. Not illuminating, so I don't want to talk about it. Okay, assuming this, see the whole proof. So, yeah, there's really not much to say about this proof. You do the intuitive thing that you can think of. You extend this embedding, try to make sure that this balance is never false negative, so that naturally we have enough room for the liability that we have, for the responsible vertices we need to embed. Now let me see how much, we have 8 minutes. Maybe we can see how we derive Feynman-Pippinger, which is really quick. Yeah, let's finish today by deriving theorem 5.1 that we promised, this Feynman-Pippinger. For when we have expansion d plus 1 times x, we can, for all sets up to size 2m, we can embed all trees on m vertices with maximum degree at most d. So this is 5.1. Now, if you stare at lemma 5.4, okay, then it's not hard to see that the expansion property from the Feynman-Pippinger guarantee this orange box expansion property here for sets between size m and 2m. So that means we can apply these, okay? But in order to even start applying for lemma 5.4 to prove 5.1, we have to show the base step of the induction, which means we have to show that a singleton vertex with no edge, if you look at the graph S, which is a singleton with no edge, this is a nice embedding. This is dm extendable. So if you prove that a singleton vertex graph is dm extendable, then after that, the inductive step is you apply 5.4 repeatedly until you finish the whole embedding, then you are done. So all we need to do for 5.1 is the base step. Okay, let's finish the proof of theorem 5.1, the Feynman-Pippinger. So, as I said, by lemma 5.4, just need to show that the singleton graph, let's say it consists of one vertex, edge set is empty, this is dm extendable. Okay, if this is dm extendable, then until S grown to full tree, we have, because the tree has m vertices, before it grown to full size, S has order at most m minus 1. So that means the external neighborhood of x, no, sorry, the neighborhood of x is at least by our expansion property from the Freeman-Pippinger hypothesis, D+1 expansion is at least dx plus s plus 1 for every x at least m, at most 2m, right? So this verified the expansion property in lemma 5.4. Okay, this is precisely the orange box expansion in lemma 5.4. Where is it? I think Sangye was doing something quite nice. He has a small window on the left where you can see some smaller picture, then I don't have to scroll down that much. But anyway, you see here, this orange box in lemma 5.4. So we just verify that. When S ground to full size, before that, we always have this from the D+1 expansion in the hypothesis. So that means we can use lemma 5.4 and we are done. So we just need to prove this base step. And this is also simple. Basically, yeah, this is okay. Actually, even though it's basic, I want to give the full proof because later the identical proof give us the ability to embed larger trees. So let's prove this here. Okay, it's actually very simple. So let's let V of S to be the singleton. Okay, and let's take a set X of size at most 2m and prove that X has non-negative balance with respect to S. Okay, need to show the balance of X with respect to S is non-negative, right? What do I write here? As, to see this, as S is empty graph, we have that the degree in the partial embedding is always 0 for all little x in capital X. That means we don't need to worry about the degree sum in the definitional balance. This implies that B, the balance of X with the blah, what did I just say? Equals to the neighborhood sticking out of the vertex set of S, which is the singleton, okay, minus D of X, right? The degree sum disappear in the definition. What is that? Well, this term is at least its neighbor minus 1, right? We subtract the singleton S, at least that. But what do we know about the external neighborhood? We know that it expands by a factor of D plus 1. Now, since X is now empty, at least 1, this is non-negative. Finish the proof. Okay. So we will conclude today. We stop here. We proved the Freeman-Pippinger. Next time, we will pick up from here to show that, to see how to do almost spanning tree in expanders and GMP. And then actually that we don't need to prove anything. Exactly what we do today give us that already. So I'm just gonna make some remark tomorrow about this and start our proof about spanning trees in random graph, okay? So let me stop here and stop at this Freeman-Pippinger theorem. Right. If there are any questions, then...
Anyone have any questions?
So this is the main lemma today.
And if no one has question, then we can finish today and then we meet tomorrow at the same time.
Okay.